they want a free body diagram for the inner block M1 with this bird's eye point of view, so I don't need to include Fn and Fg because they're not observable forces from this perspective. So I see this rope right here, T1. That's going to be a force that pulls the block inwards. So this is going to be my T1. I know that there's another string here, which is the force is represented by T2 because it's connected to another M2, and that's going to pull my block the other way, but a lot less than the one pulling inwards. Because if this was greater than this, then it wouldn't be centripetal motion, it wouldn't really be spinning in a circle anymore. Because there needs to be a force pulling inwards. The net force has to pull inwards. Okay, and now for M2, it's just going to have that T2 pulling you inwards. And it's going to be equal to this, because equal opposite reaction. Yeah, so that's A. That's B. Now, let's go to C. Calculate time period T. For the outer block M2. So, first off, I know that speed is equal to distance over time, right? Well, what's the speed for M2? They give it to us, 4 meters per second. So 4 meters per second is going to be equal to distance over time, right? Well, I want to solve for time, so I know that the time will be equal to the distance over 4 meters per second. Well, what's the distance? Well, if I want to calculate the time frame for outer block M2, we're going to look at it. You see that M2, the distance it travels, is just going to be the circumference of the circle. So, the D for M2 is going to be equal to 2 pi R2, because that's 2 pi R circumference, and R2 is the radius of the second mass. So, 0.75 meters, you can plug that in. That's going to equal 4.71 meters. So now, if I plug that in, my time period T, which I'm going to capitalize now because this was just general, but now it's respecting the problem, time period capital T, is going to be equal to what I calculated for distance, 4.71 meters, over 4 meters per second. Meters cancels out, and that's going to be equal to about 1.178 seconds. So yeah, let's see. Now, D. Calculate tangential speed for the inner block M1. Okay, so I know both these blocks follow the same motion. Like, they're both going to be spinning together. So, I know that speed is equal to distance over time, right? Well, actually, capital T to respect the fact that I'm going to use this time right here because they're moving together. So this tangential speed is going to be over that time I calculated here, but it's also going to be the distance traveled. Well, what's the distance traveled by M1? That's going to be 2 pi R again, but instead it's with R1, 0.4 meters. So, 2 pi R1 is going to be equal to 2 pi times 0.4 meters. And that's going to equal 2.51 meters, and over this time frame, so 2.51 meters, but this T over here is equal to 1.178 seconds. So that gets my tangential speed to be 2.13 meters per second. So that's the tangential speed of the inner block M1. Now, derive an expression. So I want to derive an expression for the centripetal acceleration of the inner block in terms of R1 and period T, right? Well, the general formula for centripetal acceleration is equal to v squared over r, right? And I know that the radial acceleration with respect to the inner block M1 is going to be v1 squared over r1. But I want the function to be in terms of R1 and period t, right? Well, I know that V1, as I calculated up here, is going to be equal to 2 pi of R1, as you can see here, over that time period t, which was this. So really, I can plug that in here. AR is equal to 2 pi R1 over t squared, and that's only V1 squared, so that's all over R1 too. So it's also all over R1, right? And let's simplify that. Squared is going to go into there, so it's going to be 2 pi R1 squared over t squared, and R1 is going to come up. And this is simplified to 4 pi squared R1 squared over T2. Wait, T2? Oh no, T squared. And then R1. Right, and this R1 is going to cancel one R1 from here, one R1 from there. And that gets it to be the final expression, 4 pi squared R1 over T. So yeah, that's the expression for E. Now F, we're going to find the ratio. Once we determine the ratio, AC M1 over AC M2, which is just the centripetal acceleration of M1 over the centripetal acceleration of M2. Well, I know that AC is going to be equal to V squared over R, right? So AC M1 is going to be equal to V1 squared over R1, and AC M2 is going to be equal to V2 squared over R2. Well, I've calculated those values. V1 squared is just going to be here, 2.13 meters per second. And R1 is given by the problem to be 0.4 meters. And then this has to be squared. Okay. Now for V2's expression. Well, V2, the problem gives it to us, 4 meters per second. And that's going to be squared. And the R2 is 0.75 meters. Right? And let's get the values of those. This one's 11.34 meters per second squared. This one is 21.33 meters per second squared. And dividing that, it gets me the ratio, which is 0.53. So that's F. And just to clarify, there's a squared here. I forgot that. Now for G. It wants the ratio of FCM1 over FCM2. Well, I know that centripetal force is equal to mass times centripetal acceleration. Fc equals Mach. So I can just get the mass M1 and the mass M2 and multiply them by their centripetal accelerations, which is right here, 11.34 for M1, and then 21.33 for M2. And doing that, will get me, well, M1 is 0.05 kilograms, and M2 is 0.03 kilograms. So multiplying M1 with 11.34 gets me 0.567 units, and multiplying M2 with 21.33 gets me 0.6399 units. And that ratio is 0.886. Now for H. H wants the magnitude of tension T1. Well, let's write out what tension T1 is a part of first. So I know that T1 plays a role in FC1, right? Because it's the net force of the forces going inwards that act on block 1. On that same plane, inwards and outwards. So FC1 is equal to T1 because that's pulling inwards, but it's also minus T2 because that's pulling you outwards, the block outwards. And then let's write FC2. It's just going to be equal to T2 because in looking at that M2, right, the only thing pulling it inwards is T2. So I already calculated FC2. It's FCM2, FC2. So this is what it is, and it's because of mass times centripetal acceleration. And now, to find T1, I need FC1 plus T2. So T1 is equal to FC1 plus T2. Well, this is T2. Oh, this is T2. And this is FC1, FCM1. Right? 0.567 plus 0.6399 gives me the tension force of T1 to be 1.2069 newtons. And next problem, I simply just wants the magnitude of T2, which I've already calculated to be 0.6399 newtons. And now, let's go to J. J wants the magnitude of the net force acting on M1. So basically, sum of all the forces acting on M1. However, if you look at all the forces acting on M1, you see that the FG and FN, they cancel each other out. They're not even included in this diagram because it's a bird's eye point of view, but regardless of that, they'll cancel each other out, so I don't need to worry about them in the calculation of the net force. Really, all I have is T1 minus T2. Right? So, let's do that. My value of T1 is right here. And then my value of T2 is right here. So, T1 minus T2 is equal to 0.567 units. Okay, part K. So, as I established earlier, T1 minus T2, which is the forces acting on the same plane, the inward directions, on mass 1, is equal to FC1, right? And I know that T2, the force acting on the inwards direction on that plane for mass 2, is simply equal to FC2. Now, when the mass increases, what happens to T1 and T2's magnitude? Well, first off, let's look at what T1 is. I know that if I isolate for T1, T1 is going to be equal to FC1 plus T2. I established this earlier. So, I have these two equations. T1 is equal to FC1 plus T2, and T2 is equal to FC2. Well, I know centripetal force is mv squared over r. And then FC2, with respect to mass 2, would just be m2 v2 squared over r2, right? And then same thing with FC1, m1 v1 squared over r1. Now let's look at it. You see, mass is a component of this. And you see, as the mass would, let's say, as the mass increases, as the problem says so, you're multiplying a larger value by this centripetal acceleration that's the same as before. So basically, you're just multiplying a larger number by this constant value that's no different than the centripetal acceleration we had before with the same mass. So because of this, as you have a larger mass, you're going to multiply m2, a larger m2, by the centripetal acceleration for the mass 2, and that's just going to give you a larger FC2. As this increases, FC2 increases, and as FC2 increases, T2 increases. But we know that as T2 increases, T1 is also going to increase because T1 is FC1 plus T2. But we also know that as the mass of block 1 increases, FC1 is also going to increase because, larger number multiplied by the same centripetal acceleration as before for mass 1. So basically, as the mass increases, all of this increases. And it makes sense because as we're trying to go at the same speed, but we have larger blocks, we're going to need more tension force inwards to keep those blocks in the centripetal motion because their inertia from all that mass and everything, it's going to be trying to fight outwards as we spin it around. So we need more tension to keep it inwards and keep it in that centripetal motion. So there you have it, problem K. Alright, problem L. So we want a graph that, when we graph, we can use its slope to find the magnitude of tension 2. Well, let's look at what we have first, what the problem gives us. We know that these time frame corresponds to the amount of revolutions he's traveled. So let's just write that down, because the problem tells us that. We know after 1 revolution, it's been 0.2 seconds have elapsed. 2 revolutions, 0.42 seconds have elapsed. 3 revolutions, 0.61 seconds have elapsed. 4 revolutions, 0.81 seconds have elapsed. And 5 revolutions, 0.99 seconds have elapsed. So, that's what we know. Now, let's try to think. We want something that when we graph, we can use to find the magnitude of tension 2, right? But what was tension 2 equal to? FC2. Why is that? Because when you draw the free body diagram of M2, you know that the only force pointing you inwards is T2. Therefore, we can say that T2 is the centripetal force of M2. Well, we know that the formula for centripetal force is equal to mv squared over r, right? And shaping that values to respect mass 2, we get that m2v2 squared over r2. Well, we're observing changes of time, right? And we know that the radius and mass are constant, so it makes no sense to look at that when you're graphing, right? So we need to look at velocity because that's dependent on time. Let's break up velocity. Okay, when I break up velocity, you'll go into simply displacement over time. Well, to define displacement, I'm going to look at it like this. You see, each time frame they give us, right? Each time point, you're going to travel more revolutions, right? So while you're going to keep traveling on that same circle, and you might say that displacement is going to be 0 here once you travel 1 revolution, that's not how I'm going to classify it. I'm going to classify it as displacement from the very original starting point, before, like the 0th revolution, before you travel into the 1st revolution, 2nd, 3rd, and 4th, and 5th. So if I call that the original starting point, right, then every revolution, your displacement is simply the circumference, 2 pi r, well, 2, r2, because that's the mass I'm looking at, the tension force I'm looking at, T2. Well, going off that, if every revolution is 1 circumference, then I simply have to multiply 2 pi r2 by the amount of revolutions to get the distance I've displaced from the original starting point that corresponds to each time. So, let's do that. Delta x in meters. Okay, so 2 pi r, r2, where r2 is equal to 0.75 meters. Well, let's do it. 2 pi r2 times 1 is simply going to be 2 pi 0.75, which is 4.71 meters. Well, let's move to the next one. Now it's 2 revolutions. 2 pi r2, which is 2 pi times 0.75 times 2, which is 9.42 meters. Now, 3 revolutions. 2 pi times 0.75 times 3, 14.14 meters. 4 revolutions. 2 pi times 0.75 times 4, 18.85 meters. 5 revolutions. 2 pi times 0.75 times 5, 23.56 meters. Right? Now, with this table, we have information. We can graph this, and we'll be able to get velocity, because it's going to be a position by time graph. Well, that's what I'm going to graph, actually. Position by time graph, because if we get the slope of that, right, it's simply going to be rise over run. And that's going to equate to my velocity at any given time here. And that velocity could be used to find T2 at, let's say, any given time. So, when it comes to this, I kind of spoiled the answer. The vertical axis is simply going to be my rise. It's going to be my delta x in meters. Meaning my horizontal axis is simply going to be my time, the delta t they give you here, in seconds. And with this information, you can graph it, and finding the slope of that gives you a velocity that you can use to find FC2, which equates to T2. So, there you have it. Problem well.